I've been following wafer-scale integration since the 90s. There was a company by a fellow in England, Lee, that built a machine called WASP. This was kind of a neural network machine. It had its own challenges. I then followed that we still have a big project in Europe as part of the flagship project, led by the late Karl-Heinz Meyer, to build a neuromorphic wafer-scale system. I've seen multiple instantiations of that project, as I was one of the people regularly visiting them and looking at the progress they were doing. And so it's good to now have a company that is going to tell us how they're going to solve all the problems, practical, theoretical, marketing problems, yield problems that wafer-scale integration entails. And with that, I'll let Andrew, I guess, you're the director of, you're the project, product management director, CEO, whatever that is. And you're going to tell us something about your company.
Thank you, Andreas. And good morning, everybody. I'm here today with my colleague, Xin Wang. Yes, I'm the head of product at Cerebras Systems. Andreas, I like the title CEO better. I should talk to our CEO about
okay,
changing my title to CEO.
CEO of something, CXO.
We appreciate the opportunity to talk to you today about our project at Cerebrus, building a wafer-scale processor and computer system for deep learning. We're excited to have the opportunity to share this with you and discuss together in a Q&A session about how our system, the CS1, can be used to accelerate research and development into neuromorphic systems. I was introduced to this group and this conference by my colleague Xin, who I'll ask to introduce himself in just a moment. But I will say I really like the T-shirt. I love Telluride. I think the topic and the agenda look fantastic, and I just wish that we could have visited and been with you in person. So we, of course, hope that you're all staying well, and we look forward to the chance to do that very soon. With that, Xin, if you don't mind just giving a quick introduction for yourself and what you're doing with the company, and then I'll jump into slides while you're doing that.
Thank you, Andy. Can you guys hear me? Hello?
Yeah, I hear you loud and clear. It's
yes,
perfect.
Great. Yeah, it's really nice to be back. Thank you guys. Thank you, the organizers, to invite me. So I'm a neuroscientist by training. Actually, a lot of people in the audience gave me a lot of advice along my career. Currently, I'm working with Cerebrus, and I'm going to talk a little bit about the work that we do right now and how the products we build can be actually useful for neuromorphic engineering. So with this, I give the control back to Andy.
Thanks, Xin. Well, everybody, allow me to introduce you to Cerebras System and Wafer-Scale neural computation. As you are aware, Cerebras is a computer systems company. We are based in Silicon Valley, and we are building a new type of processor and a new class of computer system to accelerate sparse linear algebra and computation for deep learning and artificial intelligence by orders of magnitude beyond what's possible with legacy general purpose processors. I am not a neuroscientist by background. By background, I'm a physicist and signal processing researcher, and came to Cerebras by way of previous work at Google, where I was doing applied machine learning research for computer vision applications. But here we are at Cerebras on a mission to transform the compute landscape by radically accelerating compute for artificial intelligence. Our company was founded in 2016 by a team of experienced and innovative experts in computer chip design, system engineering, a team that has been inventing, designing, developing, building, and delivering high-performance computing solutions into the data center for more than 20 years. Our CTO, Gary Lauterbach, was previously the chief microprocessor architect at Sun Microsystems. He and our CEO, Andrew Feldman, have been working together for more than a dozen years on multiple projects to bring high-performance computing solutions into the data center. Thanks to some smart and strategic investments from some of the smartest venture capital and investors in Silicon Valley, since 2016, we've grown to more than 220 engineers with a combined experience of more than 3,000 years in hardware engineering, from chip design all the way up to system engineering, software engineering from microcode and compiler development all the way up to user-facing frameworks like TensorFlow and PyTorch, and a dedicated team that's focused on machine learning research to help develop algorithms and methods that can take advantage of our unique computing architecture for machine learning research. And that's the team that Xin is on. So I like to start with this slide, which I think is maybe not too contentious, but we look across industries, and whether it's for neuromorphic research, web, social media, or even research in health sciences to help identify solutions to human health problems like COVID-19, AI has tremendous potential. But training large models with real-world data sets often takes days or weeks of compute time, even on large clusters of general purpose traditional processors. And so while AI has tremendous potential, it's compute limited today, constrained by existing infrastructure. And it turns out that challenge is getting worse. OpenAI recently did a study that was published in 2018 that showed that the compute demands for the largest AI training runs had grown over 300,000 times in the 6-year period between 2012 and 2018 at an exponential rate that exceeds the exponential rate of Moore's law. So what this tells us is that AI compute demands are growing at a rate that will be difficult to meet with traditional processor technologies. And so we assert at Cerebrus that a fundamentally new compute solution is needed to accelerate work in this field. Our vision for the right processor for AI, we wrote down on a whiteboard nearly 4 years ago, and it included the following tenets. First, we know that neural network computing for deep learning is a unique and compute-intensive workload. So the right processor for AI should have lots of computational resources, many cores. These cores should be flexible and programmable, but they should also be built from the ground up, optimized for tensor-based sparse linear algebra operations that are foundational to the work that they're going to do. We don't necessarily need silicon area, say, for graphics-related processing or full precision physics-based simulations, right? We need a computational engine that is purpose-built for the application it will accelerate. But AI isn't just a compute problem, it's also a problem of handling data in motion. And so we need a processor that also has high memory bandwidth and high communication bandwidth. These are areas where traditional general purpose processors are challenged in terms of accessing memory from, say, large bank of off-chip DRAM and communicating between processors in a scale-out cluster. Last but not least, this engine, we know as hardware developers, must be easy to program with the software that data scientists and ML researchers are using today. So this engine should be programmable with ML frameworks like TensorFlow and PyTorch. With those tenets in mind, at Cerebrus, we built the Wafer-Scale Engine. This is a wafer-scale integrated chip. It is nearly 60 times larger than the largest chip built previously. It's shown here at the left. Next to that previous largest chip built, the NVIDIA Volta V100. This is an 8.5 inch by 8.5 inch monolith of silicon with 1.2 trillion transistors, 400,000 individually programmable compute elements, all of which are connected directly to one another on silicon over a high bandwidth, low latency, two-dimensional interconnect mesh. And each core has its own local bank of SRAM. Total on the chip is 18 gigabytes, all accessible within a single clock cycle. This gives us many times more compute resources, memory on chip, and more than 10,000 times the memory bandwidth and communication bandwidth of a traditional processor like a graphics processing unit. I like to say that most good hardware companies are majority software engineers because it takes a significant investment in software to make a new hardware architecture easy to use. So our software team at Cerebrus has developed a software platform that is designed to translate a user's training or inference program written in a Python-based open source ML framework like TensorFlow or PyTorch, and automatically compile that into an executable that can run on our Wafer-Scale engine. Briefly, our stack accomplishes this in 4 straightforward steps. First, we extract a representation of the compute graph and translate it into an intermediate representation that tells our compiler the compute requirements and communication requirements of the user's network. Our software then automatically matches a high-performance kernel from our software library to each and every layer of that neural network. And our compiler then automatically allocates compute and memory to distinct regions on our large fabric for each and every layer of the network, thereby computing every layer simultaneously and executing your n-layer neural network graph as an n-stage data flow pipeline. And we configure that on-chip network according to the communication pattern prescribed by the user in their framework program. That execution plan is bound as an executable and sent over the network to be accelerated on our system. So the Wafer-Scale engine is programmable with today's frameworks. We have a library of high-performance deep learning ops that constitute our kernel library. And this entire stack is customizable and extensible for other applications with a set of lower-level APIs and development toolkits for you to optimize performance and build out the system to your needs. Altogether, this affords users cluster scale performance with the programming ease of a single node. So last, as our CEO likes to say, you wouldn't put a race car engine in a Ferrari, you wouldn't put a race car engine in a Volkswagen or a Pinto and expect race car performance. So at Cerebrus, after we decided on the Wafer-Scale engine as the right processor for AI, we had to think about the rest of the system that would allow it to go fast, right? The rest of the body and the mechanics beyond just the engine. So this system is that solution. And this is our product. This is what we are building and delivering today to customers' data centers. It's the CS1. It's powered by a single Wafer-Scale engine that's programmable with TensorFlow. And the system itself is designed to be easy to deploy, operate, and maintain in a standard data center environment today. It's 15 RU tall, so it's about 26 inches tall, or the size of a large dorm room refrigerator. It takes up about 1/3 of a standard data center rack. We take 20 kilowatts of power. We are air cooled, and we connect into the network over standard 100 gigabit Ethernet connections. But in order to provide sufficient data bandwidth into our processor, we have 12 of those links for an aggregate IO at the system edge of 1.2 terabits per second. Altogether, this system allows you to replace racks of legacy processor servers with a single system that's less than a single rack in size and less than 1/10 the space and power footprint of the compute equivalent cluster of traditional machines. So with that introduction to the product, I'll hand it over to Xin, who's going to talk a little bit about applications of this machine for machine learning and neuromorphic research. Xin?
Thank you, Andy. So I'm gonna give you guys a little bit a deeper dive into the CS1. But first, let me put it back in the context of neuromorphic research. I think in recent years, we see, especially in this workshop, sort of a confluence between neuromorphics and machine learning, modern machine learning, and age-old neuromorphic engineering coming from really the principles of the information processing in the brain, and necessarily that basically means specialized hardware. And recently, a lot of data-driven applications using modern machine learning techniques is really pushing it toward algorithmic generality. So I think you guys have seen a lot already in, for example, the projects in this amazing workshop. But I'm going to tell you about a story from the other side, where traditional machine learning really coming from abstract mathematical models, where most of the research for decades are done on a general purpose hardware. But recently, only like the past maybe 5 years, we see a huge wave because of the success of modern deep learning, a hardware specialization to boost the performance in this research area. And amazingly, I think there's similar things that we see here as the neuromorphic case, where some brain-like features actually emerge alongside with this hardware specialization, where maybe in the near future, there's some kind of synergistic effect that we can see. And I'm gonna give some examples here. So I think really in the end of the 2010s, I think Cerebrus' product is really a culmination of this wave of hardware specialization for modern deep learning. So I'm gonna introduce to you in the next slide. Next, please, Andy. The first of the very interesting phenomenon that we have seen in CS1 design. So next. So unlike a lot of modern deep learning accelerators, there are a lot of arithmetic innovations where you don't really use that for general purpose scientific computing. For example, mixed precision floating point arithmetic, basically half precision and a single precision is widely used in GPU. This is, of course, also used in the CS1 system. But what really differentiating us from the rest at 2020 is purely sparse linear algebra acceleration. And across the wafer, actually all the activations and gradients flowing in a deep neural network are sparse. So we don't communicate any zero values, but rather an index, neuron index of non-zero values and the value itself. So, this is kind of reminiscent of AER, but the purpose of this is really not that we are trying to simulate a spiking behavior, but rather it's coming from empirical observations in the modern deep neural networks. So activations and gradients in modern deep neural networks are usually very sparse. Even if in cases they are not sparse, very simple techniques can be applied to induce sparsity. And you can also see some uncanny similarities in the deep neural networks other than, for example, like feature learning or feature disentanglement in object recognition models, but also you see a progressive sparsification of activities along the depth of a neural network, very similar to the reduction of firing rate at different stages of the brain. And furthermore, in the future generations, we're going to support full sparse operations where parameters of modern deep neural nets can also be sparse. And we know that sparsification of over-parameterized models these days are very successful in hugely reducing the computational burden of deep neural networks. So a little bit of advertisement of the recent work that I have done using large language models these days. As an example, we showed that like in modern large models where training is usually done by a very lengthy unsupervised stage, followed by a very data efficient fine-tuning stage that's supervised, where the second stage, that is data efficient fine-tuning, can be done purely by sparsification, where the optimization can be done simply by structural plasticity without changing any synaptic weights. This is sort of an existential proof of a sparsity as a good candidate to speed up modern deep neural network training, which somewhat resemble the brain. Next. So I think the most interesting thing about the CS1 wafer scale design that resembles the brain actually comes from the architecture. So the original motivation of building a wafer scale integration is the observation that communication speed is really, really slow, orders of magnitude slower in a modern GPU cluster. So the idea is really to integrate multiple nodes on a single silicon, where communications is 3 orders of magnitude faster and also energy efficient, simply because of the fact that you just need to move fewer electrons through the huge capacitors that is the network cables. But how do we, make these, how do we really do this kind of wafer scale integration? Are we going to put a very large cores like GPUs and a small number, like a handful of them, interconnected on a wafer, or we rather choose a different design? So really, this is constrained by manufacturing defects. Even though the defects rates are way lower these days, but it's still present. So really, it is a kind of very common strategy that you see in silicon memory design, like for Flash, where you really design a very well interconnected tiny cores, and they're identical to each other with ample redundancy built in, such that you can have a logically complete communication fabric, as shown on the left-hand side in this slide, where you actually come from a physical realization that has defects. And this gives rise to a natural distributed, highly non-von Neumann computer architecture, where memory is really integrated locally into those tiny little cores. Next. So this is sort of very similar to the 2-dimensional sheet we see in the cerebral cortex, where you have identical local computing and memory elements that are the cortical columns of canonical circuits, where you can just easily scale it in a 2-dimensional way. Where so if you look at the Cerebrus CS1 system, we have 400,000 identical cores across the wafer. Next. So a brain-like architecture necessarily means a brain-like execution. So the way, since we designed this uniform 2-dimensional fabric, and each core is tiny, a large model cannot be fit in locally, so it has to be distributed. And just like cortical areas like V1, V2, V4, IT, different layers along the depth of a deep neural network will be distributed in spatially. And next, in a more realistic view below, you can see this is basically a layout of a realistic network along the wafer. The arrows actually indicate the forward paths of activation propagation. So this gives rise to a necessity of coming up with new training algorithms. So unlike in a GPU cluster, where you have a data parallel strategy, where each worker here, which is a networked device, they keep identical copies of the entire model, and you split data in a batch across different workers, where identical operations are carried out and synchronized in time. We have to use a pipelined model parallel approach, where you see each worker takes care of a single layer, and this forward and backward propagation of activations and error signals will end up not using the wafer in a 100% utilization. So we basically pipeline it, but with that, there's a lot of interesting problems that come up with it. For example, how do you deal with the variable delays of error signals? How do you deal with the variable staleness of parameters if you update parameters at a different pace? And asynchronous parameter update itself will introduce some interesting dynamics in the training process. So I'm just putting two papers, recent papers from the group in solving these problems. But naturally, you may ask, some biologically plausible algorithms maybe again relevant here for this kind of architecture. For example, local errors or synthetic gradients to break the serial dependence of the execution, or a model architecture that's parallel in nature instead of serial, such that and for example, like sparsely gated ensemble models, and backpropagation free optimization techniques that get rid of backpropagation altogether. So as you can see, the CS1 is really a good a substrate for a continuous streaming of online learning of data and novel algorithms, and a very nice breeding ground for novel algorithms. So now the question here to all of you is, if there's a CS1 in your hand, how do you like to use it? So I'm gonna, I know the answer to a very special case of this question about what Emery wants to do, just to give an example here. So in the talks, next in the talks, proceeding.
So Xin,
yes.
We have half an hour and there's tons of questions. Can you wrap up?
Yes, I have one more slide.
Mm-hmm.
Thanks.
Okay, I didn't want to interrupt you, this is Andreas, but I've been collecting the questions and we can go through them. Some of them are mine, some of them are from various people, so.
Great.
So let Xin just finish up, Andreas.
Yes, no, let's finish up, yes.
Right, so I'm just gonna give a quick example of a kind of collaborative project that Emery wants to do on CS1. So in a previous talk you heard from Emery, BPTT is really not real time, and it's offline learning that has a delay. Rather, if we do a forward mode next, a forward mode auto diff, you can use RTRL. That basically kind of gives you a good data flow in a system like CS1, where you have a continuously streamed data and online learning. But next, what you have is a good scaling with time, but a back scaling with model width. So the solution to that is really a sparse approximation to the RTRL operations, where the forward Jacobians can be approximated by sparse versions of it. So what would be the applications of this? The applications directly in Neuromorphic will be to learn and deploy spiking neural networks, which themselves are dynamical systems. Is taken from Emery's paper, where the alpha and betas and -1s are actually a dynamic parameters, where V and W are learnable recurrent parameters. So to generalize, you can think of any kind of dynamics that is known, and you can combine in a mixed mode AD simulation of dynamics together with learning based on deep neural networks. And finally, I want to advertise that there's an NSF-funded neocortex. It's called neocortex, very poetically, because there are two Cerebrus CS1s, like two hemispheres, with an HP superdome flex server, serving as a very powerful white matter that's pumping data in and out of the systems. So this is open to very soon to the general research community. If you have any ideas, welcome. And I'll conclude over here. Thank you.
Thank you.
Thank you. I think this is impressive work, and I'm going to start reading through the questions. I guess you can look at them. Toby, starting with Daniel, how many TOPS per watt and TEPS per watt does your system achieve?
Sure. So I can take that one briefly. We have not advertised the peak performance of the system in terms of flops or tops. We've found that that's a marketing number that's often abused and maybe difficult to interpret for particular use cases. What we have seen in terms of practical results is training large neural networks that may take days or weeks in single-digit hours. So we are already today across multiple application domains seeing acceleration on the order of 100x or more beyond individual off-the-shelf GPUs.
Okay, so the next question is a question by Toby. 20 kilowatt is a lot of power, like a Buchau say C. Is it is that going to be a cloud service, or what is the marketing?
Yeah, great question. Thank you. So our initial approach is to deliver these systems directly to customers that have on-premise data centers. And some of our early customers are supercomputer centers, but also we have customers that are industry commercial customers that have large data centers or even modest research clusters in a traditional facility. So our first step into the market is direct to on-premise infrastructure. However, we're also working with and talking to major cloud providers about how to expose a system like this as an instance type within their service. So that's definitely an approach that we're considering to scale and give broader access to this novel architecture.
Okay, thanks. So I have a series of questions, and essentially the gist of it is, and I don't know if you're the right person to answer that, is that I guess how much memory, most of the area in the wafer is SRAM?
It's actually an almost 50-50 split.
Oh, with digital logic. This is, I presume this is something like 7 nanometer, or what technology is this?
Sure, the first generation Wafer-Scale Engine is 16 nanometer TSMC.
Oh, 16 nanometer, okay.
Yeah.
And the other question has to do with whether it makes sense to do things in a big surface or do things in a traditional way that Intel has done with Xeon Phi, and then AMD and NVIDIA are doing now, which is 2.5D and 3D integration. You know, it takes a lot of energy to go from one node, from one point on the node to the end of the node, and then imagine to the whole wafer. It's better off to go vertically. Why is it better to do it on a flat sheet?
So without revealing too much, I can say that that the CS1 and first generation Wafer-Scale Engine are just the beginning for Cerebrus. We are already looking forward to second and third generation products and looking at 2.5 and 3D technologies, both for compute and for memory. As we look forward, we see a growing demand for compute in deep learning, but also a growing demand for more memory that's close to compute at high bandwidth. In our first generation solution, we addressed several challenges associated with not just 2D wafer scale integration, but also with packaging, powering, and cooling that device. Some of those packaging and cooling challenges in particular get a little bit more hairy at 2.5 or 3D. And so we're currently investigating how we can bring both more compute and more memory to the problem in subsequent generations.
Yeah, but then I will answer that or follow that. But then your system then looks very similar to what many other people have been doing for the last 5 years.
Yeah, but Andreas, you know, they're
Yes.
really trying to turn it into something and deploy it out there, right? A lot of other people, of course, are doing it, right? That's why it's interesting, but still,
Well, I
you know,
mean,
if they get it out
hey,
there and people use it, that'll be unique.
I'm talking about Google. I'm not talking about random
Oh, yeah.
people. I'm talking
Of
about
course.
Google and the company out of Stanford. What's the name? I forget the name.
It's impossible to talk
And
about all of
AMD.
them.
Yeah, I
Yeah.
mean, AMD, look at how well AMD has done with this technology. Anyway, the other questions is, will it support recurrent neural networks, and how do you do that?
Sure, I'll actually let Xin answer that one, but to come back very briefly to touch on the last point, I think one of the things that the wafer gives us is a larger two-dimensional extent over which we can maintain high communication and high memory bandwidth on the device. So in some sense, the physical dimensions give us a longer horizon on which to operate in a high communication bandwidth domain that you don't get when you have chiplets or many individual processors. But it is exciting to see what's happening in other parts of the community. We're definitely tracking that. So I'll pass it over to Xin to answer the question on spiky recurrent net.
Yeah, I think the answer is definitely yes. We're the kind of collaborative work that we want to do with Emre is just like that. But on the pattern that so you can definitely, like, if you train with truncated BPTT, it is like unrolling in time. So you're trading basically time, trading depth for time. So you can basically have like instances that shared weights laid out on the wafer. But rather a more interesting way would be to have some kind of real-time learning, which you have only one instance of all the weights and stream data through it.
I'd like to hear the question from Chang, especially the sparsity, you know, since we like sparsity a lot, the question about sparse gradients. And you guys are really pushing the idea of activation sparsity here, right? In a practical way.
Yes, and delta sparsity as well. I mean, you know, a major source of activation sparsity is really coming from you know, activation functions like ReLU, typically. And also a lot of in a case where you have, for example, like saturating, squashing activation functions, you can have even more sparsity in the backward.
But do you see the specific question from Chang there? I don't know if you see the screen, right? There's a question from Chang Gao, right? It's
okay.
I wonder what sparsity level you can achieve in gradients and what speed up you can get from it in training. If gradients are extremely sparse, does it mean the network parameters are barely updated, actually making the training slower?
Actually,
maybe the question doesn't, maybe we don't quite understand what you mean by, yeah.
Right, so in many cases we see a high level of sparsity in the gradients, but it doesn't mean necessarily a lower norm. So the non-zero components can still be large, I think.
We have a couple other questions. Can you say a little bit more about the interconnection between cores? And yeah.
So I'll give this question to Andy, his product detail.
Sure. So the interconnect between core is just a short direct wire. We also have a skip connection. And we worked very closely with TSMC to extend that direct core-to-core communication within a reticle to be able to have communication lines that cross the reticle boundaries. So that for us was the first enabling technology step towards wafer-scale integration. And we employ, yeah.
Just to follow up on that, what's the bandwidth of your wires? How many wires do you have going from a core to a core?
I'll have to double check on that. The aggregate bandwidth for the full array is 900 petabits.
No, I'm asking about between cores.
Yeah.
You're running wires. How many? 100, 228,
Yeah.
512?
I'll have to double check on that for you.
Okay,
Andrea.
if you can say that would be good.
I think it's time now to move on to our next talk.
Well, okay, thank you guys. And there's plenty of questions. And if you guys don't mind